Allsop, also from Monash University, and he's going to speak about a problem that he solved, which was a question by Falconer on loop isotopes, and it also solved the problem of the previous speaker. Over to you, Jack.
Thank you. So today I'll be talking about a problem on quasigroup varieties. What I'll be presenting was done in my honours project with Ian Wallace. So the project was on a problem in Latin squares, and then once we'd solved that problem, we realised we could use our results to tackle a problem on quasigroup varieties by Falconer. So the first half of the talk will be about Latin squares, and then the second half I'll talk about quasigroups. So I'll start with just the definition of a Latin square. Let n be a positive integer. An n by n Latin square is an n by n matrix of n symbols such that each symbol occurs exactly once in each row and column. So there's an example of a 5 by 5 Latin square whose symbols are the integers 0, 1, 2, 3, 4. And throughout the talk, the symbols of any n by n Latin square will be 0, 1, n minus 1. And the rows and columns will also be indexed by 0, 1 up to n minus 1. And so I'll define what we call a conjugate of a Latin square, but I'll just say that it's a different type of conjugate than the usual algebraic sense of a conjugate. So we can think of an n by n Latin square as a set of n squared triples of the form RCS, where R indicates the row of the Latin square, C indicates the column, and S indicates the symbol in row R and column C. And in some ways, this way of thinking of a Latin square isn't as nice because you don't get the visual picture of a Latin square, but it has some benefits. Mainly, it highlights the symmetry between the rows, columns, and symbols of a Latin square. And that leads to this definition. So let L be an n by n Latin square, then a conjugate of L is a Latin square obtained from L by uniformly permuting the elements of each triple. So because there's 6 permutations on 3 elements, each Latin square is 6 conjugates, and we label each conjugate by a one-line permutation, which gives the order of the coordinates of the conjugate relative to the order of the coordinates of the original square. So, for example, the 1, 2, 3 conjugate of a square is itself, and the 2, 1, 3 conjugate is the matrix transpose. So let L be an n by n Latin square and let I be less than j, then we can consider row I and row j of L to be a permutation in 2-line form, which we call the permutation mapping row I to row j, which we denote by Rij. And we call the set of all such permutations the set of row permutations. And we can also define column permutations similarly, and taking the matrix transpose of a Latin square interchanges the row permutations and the column permutations. So just an example, on the left, this is the row 0 and row 1 of the previous Latin square. So considering that as a 2-line permutation, that is the permutation R01 of that square, which in cycle notation is the 5 cycle on the right. And we call a Latin square row Hamiltonian if all of its row permutations are full cycle permutations. So we can construct a simple family of row Hamiltonian Latin squares using group theory. So we know that the Cayley table of a group is a Latin square, and this theorem says that the Cayley table of a group forms a row Hamiltonian Latin square if and only if the group is cyclic of prime order. So the tables of cyclic groups of prime order give us a simple family of row Hamiltonian Latin squares. So another definition, for a Latin square L, we let nu of L be the number of conjugates of L which are row Hamiltonian. And for a family of Latin squares where each Latin square in the family has the same value of nu, say nu equals c, we'll say that that family has nu equals c. And then because each Latin square has 6 conjugates, we know that nu is an integer between 0 and 6. And this lemma of oneness tells us that, in fact, nu actually has to be even. And Latin squares whose conjugates are all row Hamiltonian are of particular interest. We call these Latin squares atomic. So, for example, we saw that the Cayley table of cyclic groups of prime order are row Hamiltonian Latin squares, but actually they're atomic, stronger property. They're all their conjugates are row Hamiltonian as well. So there were 7 previously known infinite families of row Hamiltonian Latin squares, but every Latin square in these families has order either p squared, or 2p minus 1 for an odd prime p. And every Latin square in these families also has either 2 or 6. I'll just mention that row Hamiltonian Latin squares have connections to something in graph theory called perfect 1 factorizations, which I won't go into for time reasons, but of these 7 infinite families, 6 of them come from these perfect 1 factorizations in graph theory. And so we constructed an infinite family of row Hamiltonian Latin squares with nu equals 4. And before I define this family, I'll just talk about a particular type of Latin square. So this Latin square on the slides has some nice structure. It's an example of what we call diagonally cyclic. So an n by n diagonally cyclic Latin square is a Latin square which has a cyclic automorphism of order n. And as a result of this, for an n by n diagonally cyclic Latin square, the symbols on any broken diagonal, which is just a diagonal which wraps around the square, the symbols on these broken diagonals form a sequence of consecutive integers mod n. So the highlighted cells on this square here, they're a broken diagonal of this square, and you can see that the symbols form a sequence of consecutive integers modulo 11. And so now I'll define the family which we studied. So let P be a prime which is 1 or 3 mod 8, then define a P by P Latin square, which we call LP by the formula on the screen. And we note that by result of one less, we know that these are well-defined Latin squares. The example of a Latin square on the previous slide was the square L11. And actually, every Latin square in this family is diagonally cyclic. So you can see that the ijth entry, the quantity j minus I tells us which broken diagonal of the square we're on, and then the entry depends on whether this quantity is a quadratic residue or a quadratic non-residue. And Wanless conjectured that this family has nu equals 4, except for L3 and L19, which are known to be atomic. And it had been verified that nu of LP was 4 for all primes less than 10 to the 7 when P was 3 mod 8, except for 319. And it had been verified that these had nu equals 4 for all primes less than 3000 when P was 1 mod 8. And we showed that these squares had nu equals 4 for all primes other than those 2 exceptions. So the first step in showing that these Latin squares had nu equals 4 is to show that they are row Hamiltonian, which to do by the definition, you have to check every row permutation. But this result from Wanless gives us simpler sufficient conditions to conclude that LP is row Hamiltonian. So when P is 1 mod 8, it suffices to show that the row permutations R01 and R0C are P cycles, where C is some quadratic non-residue. And when P is 3 mod 8, it suffices to show that the row permutation R01 is a P cycle. And I'll just say that this lemma, it's due to the fact that these Latin squares have a large automorphism group. So I'll briefly discuss how we showed that the Latin square LP is row Hamiltonian when P is 3 mod 8. So we know that we just have to show that the row permutation R01 is a P cycle. And to do this, we use the result of Beck. So given a permutation sigma in Sn, you can define a symmetric matrix A sigma over Z2. The definition of this matrix is a bit technical, so I won't define it, but Beck showed that the permutation is an n cycle if and only if A sigma is non-singular over Z2. And I'll refer to the matrix A sigma, where sigma is the row permutation R01 of LP. I'll refer to that by AP. So this is the matrix A11, and this has some nice structure. So if you look at the highlighted rows, which are rows 3 and 4, and note that 3 and 4 are quadratic residues modulo 11, then these rows agree on all columns except for column 9. And actually, it's true that whenever you have consecutive quadratic residues mod P, their respective rows in the matrix AP differ on only one column. Also, if you look at the red rows, row 7 and row 8, and note that 7 and 8 are quadratic non-residues mod 11, then these rows only differ on columns 7 and 8. And yeah, it's true in general that whenever you have consecutive quadratic non-residues modulo P, their respective rows of AP differ in exactly 2 spots. And so we use this structure to show that these matrices AP were non-singular. We showed that when you have one of these 2 situations, when consecutive rows differ in either 1 or 2 spots, you can choose 2 rows to delete. And then delete the same 2 columns to obtain a smaller symmetric matrix over Z2. And we showed that you can choose these rows so that the determinant mod 2 is preserved. And then we showed that you can always choose such, you continually do this until you reached a 2 by 2 matrix with determinant 1. And so that showed that the matrix AP is non-singular. And so combining Beck's theorem and Wanlis's lemma, that shows that LP is row Hamiltonian when P is 3 mod 8. And then to show that LP is row Hamiltonian when P is 1 mod 8, we use very similar ideas. And so once we knew that these squares were row Hamiltonian, we knew that nu of LP was either 2, 4, or 6. And so the next step to showing that these had nu equals 4 was to show these squares are not atomic except for L3 and L19. And to do this, we showed the existence of a row permutation of the 3-2-1 conjugate of LP, which was not a P cycle. So here we've got the 3-2-1 conjugate of the Latin square L11, and the highlighted cells show us that the permutation R01 of this square contains the 3 cycle 875. So this conjugate of L11 is not row Hamiltonian, and so L11 is not atomic. And we showed actually that for all P other than 19, every row permutation of the 3-2-1 conjugate of LP contained a 3 cycle. And so that showed that LP was never atomic other than L3 and L19. So we knew that nu of LP was either 2 or 4. And then finally, a result by Wanlis, which concerned the symmetry of Latin squares, which are of the same type as ours. That told us that nu could never be 2 for our Latin squares, and so we knew that allowed us to conclude that nu of LP was 4, except for those 2 exceptions, which was our goal. And now I'll discuss how we use this construction of these Latin squares to solve a problem stated by Falconer on quasigroup varieties. So first I'll define a quasigroup. So let Q be a set with a binary operation multiplication. Then we call this pair a quasigroup if for all A, B, and Q there are unique X, Y, and Q such that equations 1 and 2 on the slide are satisfied. And we call Q a loop if there's an element of Q which acts like an identity. And so finite quasigroups are an algebraic equivalent for Latin squares in the sense that the multiplication table of every finite quasigroup is a Latin square, and also every Latin square is the multiplication table of some finite quasigroup. And so before I can state Falconer's problem, I'll need to give a few definitions. So we call 2 quasigroups Q and P isotopic if the multiplication table of Q can be obtained from that of P by a permutation of the rows and columns, as well as a permutation of the elements of P. And in this case, we call P an isotope of Q and vice versa. And when Q and P are loops, we call these loops isotopic if they're isotopic as quasigroups. And in that case, we call P a loop isotope of Q and vice versa. Next definition. So let E be a set of identities. Then the variety defined by E is the set of quasigroups satisfying the identities in E. Similarly, the loop variety defined by E is the set of loops satisfying the identities in E. So, for example, the variety defined by the associative identity is just the set of all groups. And now I'll define some particular types of varieties. We call a variety or loop variety anti-associative if the only group it contains is the trivial group. We call a variety isotopically Q-closed if it's closed under taking isotopes. And we call a loop variety isotopically L-closed if it's closed under taking loop isotopes. All right, so we can now state Falconer's problem. So Falconer asked if there exists a non-trivial anti-associative isotopically L-closed variety, and we were able to solve this problem using our Latin squares. So before I define the varieties which we use to solve this problem, I'll just define these maps, the left and right translate maps. So let Q be a quasigroup and X be an element of Q. We define the left translate by X to be the map which is multiplication by X on the left, and we define the right translate of X to be multiplication by X on the right. All right, now let P be a prime, which is 1 or 3 mod 8, but which is not equal to 3 or 19, and then consider these two identities. So if a loop Q satisfies the first identity, this is equivalent to saying that the multiplication table of Q is row Hamiltonian, which is equivalent to saying that every element of every loop isotope of Q has left order dividing P. And then if Q satisfies the second identity, that's equivalent to saying that no column cycle of the multiplication table of Q is a P cycle, which is equivalent to saying that every element of every loop isotope of Q has right order coprime to P. And we showed that the loop variety defined by these two identities was a non-trivial anti-associative isotopically L-closed variety. So firstly, because these identities concern the left and right orders of every element of every loop isotope of a loop, it's not too hard to see that this variety is closed under taking loop isotopes, so it's isotopically L-closed. And then also in a group, the left and right orders of an element are the same. So if a non-trivial group satisfied both of these identities, then the first one tells us that the order of every non-trivial element is P, and then the second tells us that the order of every non-trivial element is coprime to P, which is obviously a contradiction. So we know that the only group which satisfies both of these identities is the trivial group. So the variety defined by these identities is also anti-associative, and it just remains to show that it's non-trivial. And we did this by using our Latin squares. So for the Latin square LP, we have shown that LP is row Hamiltonian, and we've also shown that no row permutation of the 3-2-1 conjugate of LP is a P cycle. And it's a simple step to go from our Latin square LP to a Latin square which is the multiplication table of a loop, which is row Hamiltonian, such that no column cycle is a P cycle. So the loop we construct in that way, it's a loop of order P, and it satisfies the two identities. And so we showed that the variety defined by these identities, the loop variety defined by these identities, is non-trivial as well. So that demonstrated the existence of a non-trivial anti-associative isotopically L-closed variety. And actually for each prime, you get a distinct variety. So we've actually showed the existence of infinitely many such varieties. So just to summarize, we constructed an infinite family of Latin squares with nu equals 4, and in doing so we proved a conjecture of oneness, and this allowed us to construct infinitely many non-trivial anti-associative isotopically L-closed varieties which solved the problem of Falconer. And then Falconer's problem suggests a direction for future research. So to solve that problem, we constructed a loop Q such that every element of every loop isotope of Q had left order N and right order M, where N and M were co-prime. And so that suggests considering the following problem: given any co-prime integers A and B, can we construct a loop such that every element of every loop isotope has left order A and right order B? Yeah, and thanks for listening.